So good afternoon, everybody. My name is Jonathan Pearce from the British Geological Survey. Welcome to this webinar from the ECCSEL Accelerate project, which is on the monitoring of technology or monitoring technologies for CO₂ capture and storage. So thank you for joining us today. I'm going to be your chair, and I'm just going to share my screen. I'm not sure if you can see my screen at the moment. You should be able to see it, I believe. Somebody give me a thumbs up to confirm. Thank you. So yes, you can see my screen. I shall make this into presenter mode for you all. And so yes, this is the 9th in a series of webinars that the ECCSEL Accelerate project has been conducting. Just some housekeeping rules to start off with. If we can, please keep yourselves muted with your video cameras off when you're not speaking. We're going to run through the presentations that we've got for you this afternoon, and then there will be opportunities for you to ask questions. Please put your questions into the chat as we go, or into the questions box at the bottom of your control panels, and I will try and feed those to the right people as we go through. So just a few words of introduction about the ECCSEL ERIC, as we call it, to give you a bit of context. So ECCSEL is the European CO₂ carbon dioxide capture and storage laboratory infrastructure. It is an ERIC, which is a European Research Infrastructure Consortium. So it's a legal entity that has been created by 5 countries. It's led by Norway, in which the seat, as we call it, the operations center, is hosted at NTNU in Trondheim. And we basically provide open access to well over 80 research facilities across Europe that's operated by 23 research facilities. And so these are all dedicated to undertaking research. These facilities vary in size and scale, but are all dedicated to enabling researchers to undertake research in all aspects of CO₂ capture, transport, and storage. And obviously CCS, I'm not going to explain what CCS is, but essentially what we're aiming to do here is to meet current European targets for reducing CO₂ emissions through CCS as one of the solutions for mitigating climate change. So as part of that activity, the ECCSEL ERIC has a project, an EC funded project, which is called Accelerate. This is due to finish at the end of this current year, this calendar year, in December of this year. And we have a budget of about 3.5 million euros, as it says here. And the Accelerate project is really to help increase the sustainability of ECCSEL as a whole. It's designed to create activities and build relationships with industry to help them access some of these research facilities. We are actively exploring collaborations internationally beyond Europe's borders. And we're also exploring ways that we can expand our services to include utilization of CO₂ as well. We also want to encourage other member states to participate in ECCSEL, and we're having a number of conversations and discussions about that at the moment. And also we want to increase the involvement of industrial users of our facilities as well. And we've seen some successes in that area over the last couple of years. As part of the Accelerate project, then we are communicating, disseminating information about ECCSEL to a wide number of different stakeholders. This includes this webinar series. It also includes some specific workshops that are being held in conjunction with some of the summer schools. And also we've undertaken a number of training courses to help both users and research facility owners understand and better access and improve their offer. So coming to today then, we have 4 speakers for you, running for approximately 20 minutes or so, 20 minutes each per pair of speakers. The first is going to be Professor John Gibbins, who is the director of the UK CCS Research Centre based at the University of Sheffield, and he'll be followed by his colleague, Professor Hughes, as a senior lecturer at the University of Sheffield. And then two of my colleagues from the British Geological Survey, Helen Taylor-Curran, who's a senior geochemist, and then Ceri Vincent, who among many other activities happens to be the president of CO₂GeoNet, which is a large network of researchers on CO₂ storage. So with that, I will stop sharing my screen. I will change the presenter to yourself, John.
Right.
And I will confirm that. And now you should have the ability to share your screen and show your presentation. And if you could, you and Kevin, if you're able to speak for about 20 minutes in total, then I'll give you a nod when those 20 minutes are running out. But the floor is yours now, John. Thank you.
Can you see my screen okay?
Yes, we can. Perfect.
Okay, so I'm going to talk about what it says, health, safety and environmental aspects of amine capture. Let's see. So big issue here is nitrosamines, which are highly carcinogenic substances that can be formed from amines by, you probably can't see a mouse, but it's by adding NO onto them. And these have received quite a lot of attention for atmospheric emissions, and Kevin's going to tell you more about that. So this is adding amines to the atmosphere, and then having them react in the atmosphere, as well as the potential direct emissions of amines from a capture plant. But something that isn't receiving as much attention is nitrosamines building up in the solvent. So you can build up nitrosamines in the circulating solvent, may have issues for operator exposure, unintended releases, and also the waste streams like reclaimer residues can contain quite a lot of nitrosamines because you're pulling them out of the amine. And then there's a fundamental issue involved here, which is primary amines versus secondary amines. Primary amines, monoethanolamine, some of the acrylamines, won't form stable nitrosamines themselves, only their degradation products will. Whereas secondary amines, most notably piperazine, will form stable nitrosamines directly. They're in fact very good NO2 scrubbers. They're widely used because they give you somewhat reduced energy consumption, but they come with this issue. One very telling thing is that there's very, very few, I could add a few more varies, nitrosamine measurements reported in post-combustion capture tests, even for non-proprietary amines. People just don't measure how much nitrosamine they've got circulating in their solvents in a lot of pilot tests. They don't measure how much is coming out. One of the things you can do is to reduce NOx levels in the flue gas, which will reduce nitrosamine formation rates. But ultimately, if you don't get rid of them somehow, they'll just build up. The secondary amines, which are the worst problem, the countermeasure is to run the solvent regeneration in the stripper at high enough temperatures, above 150 C for piperazine, to break them down. It may not be so feasible for blends that contain piperazine, which I'm sure there are some in the proprietary solvent portfolio, because of thermal stability. Just by way of example, one of the rare sets of results that was reported was for tests at Test Centre Mondstadt on Caesar-1, a piperazine AMP blend, and this ended up after a relatively short test period with 0.4% by weight, absolutely astronomical amounts of nitrosamines in the circulating solvent. If you've got primary amines, you don't have to worry so much about stable nitrosamine formation, as I say, from the amine itself, but you do need to remove precursors, so you've got to be able to reclaim them. And depending on the solvent, you may have to reclaim at a higher or a lower rate. Probably MEA, you'd have to reclaim faster than if you're using an aqua solvent, but the costs and the overall implications are probably pretty similar. So just emphasizing the importance of, of solvent management in general, I'm sure you're all familiar with Boundary Dam Unit 3, which was the first post-combustion, large-scale post-combustion capture plant in the world. You can see the capture plant on the right of the frame. And the second one, large one, was Petronova. and you can see the carbon capture facility sort of in the middle. Very large facilities, but Boundary Dam has had, at least for a long time, very high solvent management costs, and Petronova at the moment isn't working. It was supposedly closed down because oil prices are low, but they've come back up again and it hasn't restarted. This is just shown here. And look at the bar charts. The variable operation and maintenance costs are the purple blocks at the top, and that's basically solvent management. And you can see that solvent management costs reported in this GCCSI publication are in excess of $30 per tonne of CO₂ at Boundary Dam, and around about $10 per tonne at least at Petronova. And it's interesting to see these costs because you see the fuel cost for capturing CO₂, which is the energy that everybody's been worried about, is actually dwarfed in comparison to the solvent management costs. So if you get the slides, you can look at the actual numbers, but there's some serious issues here with the cost of managing solvents, both for emissions and also just for keeping a working inventory and how much solvent you've got to add to do that. So some key priorities for amine management. It's not clear what's happened, and there's much higher non-fuel operating costs than expected. So obviously, key priorities to sort this out. The first one is if projects get government funding, they should report problems, frankly, so that industry-wide learning is possible. And then the second priority is test properly to avoid solvent-related surprises and have backup options available. And that means doing representative pilot tests on your actual flue gas if you don't have a reference plant. And people say, oh, I've got a guarantee, but the guarantee is usually a fraction of the license fee, which is a very, very small fraction of the total project value. If it all goes horribly wrong, you've basically got no comeback. And also, if it all goes horribly wrong with solvent management, you're paying the person who's offering you some liquidated damages a lot more money for solvent replacement costs, probably. So it's probably a wash for them. How you can get satisfactory environmental performance, I'm just going to go through the headlines. So pick the right solvent, A. B, reduce degradation and added impurity rates, so basically clean up the flue gas, but that'll only work so far. So you actually have to trap potential emissions and exit too, and you have to reclaim. And one of the things that people don't do often enough is check that the solvent has low energy, yes, desirable, stability, yes, desirable, but is it reclaimable? Can you actually clean it up? Because if you can't, it'll look good for a while, but sooner or later, it will cause problems. So the conclusions, the main concern, the health, safety, and environmental issues really is the conversion of amines into carcinogenic nitrosamines and direct emissions of those. The allowable levels in the environment are too low to measure directly, so they have to be estimated by modelling, as Kevin will explain. There is also this extra concern of accumulation in the solvent inventory and the waste streams. This is likely to be a big problem. The UK, for example, compared to Norway, which will have a few isolated capture plants, is likely to have 10 or more of these capture units in a single airshed in any of our clusters. So they'll have to be included in impact modelling. You have to look at all the sources, model it all. So it's actually very important to understand what's going on and to get people to tell you what they put in the environment. And there's a range of measures to control emissions, but actually the most important one is start out with the right solvent, because as we've seen actually, I think on Boundary Dam, if you don't start out with a manageable solvent, it's very, very hard to overcome the problem. Thank you.
Thank you very much, John. If you're able to stop sharing, I will change presenters now to Kevin.
How do I stop sharing?
I think I've done it for you by default, actually, John. But
Yeah, I did as well. Thanks.
Kevin, over to you.
Okay. Hi. This looks fairly straightforward. I don't know if you can see the screen or not.
Yes, we can. Thank you.
Okay. So, good afternoon. So, as Jonathan explained, My name is Ceri. I'm a senior lecturer in the Mechanical Engineering Department at Sheffield, and I'm going to say a little bit about atmospheric amine chemistry. This is work that we've been doing in the past year or so, mainly by Christopher Parks, who's our research associate who's employed in this area. So in terms of the approach undertaken, the majority of the work so far has focused on the use of the Gaussian 09 software package to calculate from first principles the molecular structure and the energetics of the species of interest. The details below just say a little bit about the options that are used within the Gaussian package. You don't really need to know what they all mean. Suffice to say that they're consistent with current publications in this area, and they would represent a compromise between accuracy and computational costs. I think depending on the problem looked at, you're looking at hours to weeks of computational time for the sorts of calculations that Christopher has been doing. And the outputs from them can then be used to extract rate coefficient data to be used within the ADMS model for atmospheric simulation. Say a little bit about the molecules that have been studied so far. That there were 3 categories. Obviously, MEA being the base case for which most studies have been performed and most literature data exists. For Christopher's modeling purposes, some simple amines that are relatively easy to study, so you can test and evaluate the methods used. And then for relevance to some future work, more complicated amines for which some work already exists in the literature concerning their degradation and use. And for each amine studied, a number of reactions were investigated corresponding to the types of reaction that you need to use within the ADMS software, mainly the radical abstraction from the initial amine, imine formation from the radicals produced, and then nitrosamine and nitrosamine formation as well from the radicals produced. This is just an example of some of the Gaussian output for the reaction of, in this case, AMP with OH. And what we have here is a potential energy surface. We've got the Gibbs free energy of formation on the left hand, on the y-axis here. The numbers are all relative to the reactants, in this case, AMP being OH being set to 0. And we can see how the reaction progresses. There are a variety of transition states corresponding to the different abstraction places that the OH can nab a hydrogen from the initial reactant, and then the corresponding products and their energies as well. The transition state properties are the most important because they would dictate which route is likely to be most favored in the reaction, and also the numbers can then be used as a basis to extract rate coefficient data for the ADMS model. And the table here is just summarizing the transition state barriers for the formation of the possible radicals by the attack of the status species OH, O2, NO2, and chlorine on the initial on the species of interest. The data here then form the basis for extracting via a transition state theory method rate coefficients for the actual reaction, which is what we would need for the ADMS software. This table is summarizing, I'm not going to go into detail about every number, it's just there for record. It's summarizing the data for all of the major species investigated, the OH abstractions, NO abstractions, chlorine abstractions, the nitrosamine and imine formations from the various amines investigated so far. In terms of potential further studies, a larger library of data has been created from around 70 species, looking into amine radical formation at multiple sites within them. This is still ongoing. It could lead to a more comprehensive ADMS library should all of the other reactions be investigated, in particular the imine formation, the nitrosamine formation, and so on. For those of you that are unfamiliar with the ADMS software package, this is just illustrating how it handles the amine chemistry. Basically, it simplifies it into just 5 reactions encapsulating all of the amine chemistry, 4 of them actual chemical reactions, and then 1 photolysis reaction. And if you're using this software, what you have to do is then provide it with a rate coefficient parameter for each of these reactions. And where you get that from, well, that's your problem at the end of the day. And hopefully you have something that's meaningful and can be verified in some form or other. Just to illustrate some of the benchmarking studies that Christopher has performed so far. What is done so far is keep the reactions 2 onwards, 2, 3, 4, A and B constant, branching ratios constant, and at fixed values of OH and O2. And he's just looked at the variation by plus or minus a factor of 10 in the initial rate constant for the OH abstraction reaction. This is just a very simplified illustration of what he's got out of it so far. Nominally for a 100-meter stack, 10 meter wide. 1 day of meteorological data and concentrations of the given amines, nitrosamine, and nitramine over this 24-hour period, I think in micrograms per cubic meter units. So to conclude what I'm going to say so far, Christopher has completed most of his Gaussian calculations. There are still some to do, particularly nitrosamine formation, to improve on what he's done so far. He's used the data that he's got to generate the relevant values for use within ADMS. There's still a lot that he has to do, to be honest, in terms of actually using ADMS and comparing it on various situations with MEA and other amines. And from the Gaussian work that he's done so far, there's the potential to extend this to a much larger body of amines should the need arise. So thank you for your attention.
Thank you very much, Kevin. There's been no immediate questions in the panel for any of the attendees. So I think what we'll do is we'll move straight on to the other end of the chain, let's say. And I will change the presenter now to Ceri, who's going to be talking first about some of the monitoring options we have in CO₂ storage and their rationale, let's say, following on from the capture side. So Ceri, I believe you should be able to share your screen, which you're doing. The floor is yours. Thank you. I think you're muted.
Nearly got it right. Okay, so I'm hoping you can see my screen and that the slides will move for me. So let's see what happens. So I'm going to talk.
Screen, yes.
Did you see the slide change just then?
We did, yes, thank you.
Excellent. All right. So Firstly, I'm going to talk about why we monitor CO₂ storage sites, and I'm going to focus on the technologies for monitoring the subsurface. And Helen's going to follow me with talking about what happens when you're looking at surface in the unlikely event that a storage site were to leak. So why do we have to monitor CO₂ storage sites? Well, we monitor for environmental reasons. So we're trying to tackle climate change. Let's check that it's actually working. And also for health and safety requirements to make sure that there's no unwanted emissions at the surface. We need to show the site is conforming, including answering questions from the public, and also for financial reasons. So we might be receiving carbon credits through the European Trading Scheme or some other local arrangement. So we need to conform in Europe with the European Storage Directive. So we have to show that we can demonstrate that the CO₂ is safely contained in the reservoir. We have to monitor potential containment risks. So is there anywhere where we think it would be more likely that leakage might occur, and what should we do to make sure that we can see that's not happening? We have to show the site is behaving as expected, identify and remediate any non-conformances, and finally enable site closure and handover. So we're going to need a strategy that's got a clear statement of aims, justification of why we've selected certain monitoring technologies, how frequently we're going to monitor, which technologies, what's the area that we're going to monitor, and to make sure we've got good record keeping and reporting. And these are all going to vary depending on the site. It's going to be very risk-based, site-specific monitoring. So there's some overlying guidance, but we have to make sure specifically how we're going to demonstrate that our site is behaving as expected. So what are we trying to monitor in the subsurface? Well, we're trying to see the free CO₂ plume trapped in the reservoir. So the CO₂ is buoyant at the depths where we're storing it, typically below 800 meters. So we expect that CO₂ to slowly migrate towards the top of the reservoir. It might get trapped under small permeability barriers, like little layers of shale within our sandstone. And as it rises to the top, some will be trapped by capillary forces, so a little bit will be left behind as the CO₂ plume migrates, and the CO₂ will be slowly trapped by chemical reactions, dissolved into the pore water, and eventually sink to the bottom as a heavy fluid. So we've got quite an interesting collection of things that we can monitor, so we can look for changes in the physical properties, changes in the electrical properties, changes in the chemical properties, and it's just a question of how do we do that. So we've got a whole host of technologies that we can choose from. We've got some of these are well established from the oil and gas industry, some are specific to the CO₂ storage industry, and we're going to select something that's most efficient for the leakage risks that we want to monitor and the physical properties of our storage site. So I'm only going to give a few examples, because if I were to talk about monitoring technologies in the fullest sense, we'd be here all day, but I'm just going to mention a few kind of highlights. So we could consider repeat geophysical surveys and arrays. So geophysics is indirect. We're looking at the properties of the subsurface and using that to infer where we think the CO₂ is now and to demonstrate that there's no leakage. So we might undertake large-scale seismic surveys. So they might be 2D, as in a line, 3D, as in a grid, or 4D, as in we keep going over the same area, repeating our 3D grid. There's also very emerging technology of optic fibres, which is a really fast-growing field, and the sensitivity and accuracy of this technique is improving very rapidly, to the point where downhole fibres could be used in place of conventional geophones, and some storage sites are proposing to do this as an effective long-term monitoring strategy. And we can use gravity surveys looking to detect density over time, electromagnetic surveys, and we might have permanent installed sensors or undertake repeat surveys. And we're also interested in microseismic surveys, which will help us locate and quantify any microseismic, so any tiny tremors in the subsurface. So that's quite important to make sure that we can show the site's behaving as expected, we can answer any queries from the public, and we can show that our site is behaving as expected. We're not having negative consequences on the surrounding environment. We also have some more direct methods that we might deploy. So we have rock cores collected from the reservoir and the cap rock to characterise the site, looking at how the CO₂ and the pressure will affect the reservoir and the seal. We could undertake fluid sampling, which gives us a direct measurement of the CO₂ concentration in the reservoir. So it's a little challenging to take fluid samples because we have to maintain that pressure in the subsurface. Otherwise, when we bring this fluid sample to the surface, it will degas in the same way as it does when you open a bottle of fizzy water. We might also undertake fluid sample from nearby groundwater wells, particularly if we're onshore, to demonstrate that we're not damaging a local important resource. And of course, we've got geophysical logging, where we put tools into the hole to detect changes in the physical or electrical properties of the subsurface. So the CO₂ will, as it dissolves, creates acidic water, and that changes the electrical properties of the subsurface. So we might be looking for those changes as well. We can also consider putting sensors on the inside or outside of the tubing or casing. So one of the key considerations for this is, although it means that you can still use the tubing and you've got tools on the outside which are not interfering with your operations, there's a risk of all of these extra cables introducing leakage pathways. And we have to think about the sensor lifetime. So after you've put something on the outside of the casing, in the case you're looking here, this is just a very shallow well. There's only that single tubing going into the hole, and we put the sensors on the outside, but after that tubing is cemented in place, you're not getting it back out. So you have to think about how long your sensors are going to last. Pressure and temperature is really critical in terms of safety and understanding that the storage site is behaving as expected. So we can use that to look at mechanical integrity of the reservoir and the wells, providing information on injectivity, and monitor the casing and the cement integrity. We also find that optic fibre is being more increasingly used. So it's used for distributed acoustic sensing, which detects strain along the fibre, which would be typically along the casing. So you're looking for changes in the reservoir that sort of stretch the fibre. And we're looking for distributed temperature sensing. So temperature can tell us an awful lot about what's happening in the reservoir, where our CO₂ is. Microseismic often requires a dedicated well array, so that might be something extra to consider depending on how much we're monitoring the reservoir, how much detail we need. And there's also some interesting research and development looking at little sensors that you can pop into the cement. So there'd be self-contained capsules that go in the cement, and you run a tool that activates them and checks the readings down the hole. So there's kind of a whole range of tools going from the really well developed and proven to research to how can we do this more effectively and more cheaply. So just to give a couple of examples. So here's an example of measurement, monitoring and verification from the Sleipner site. So on the top you can see the sort of size view of these are reflections of sound from the rock layers. And what we're seeing is that as the CO₂ is injected over time, we see that this is changing the properties of the rocks, and we see this bright area. So we can see that the injection point's down here, the cap rock's here. It does look like the cap rock's going up, but that is an artifact of this technique because you're not actually seeing depth, you're seeing sound. So the CO₂ is changing the properties in the reservoir, and we see it being safely trapped there. And there's also some more direct monitoring. This was from K12B, looking at pressure and temperature in the reservoir. So there are also some interesting research projects looking at how you could use pressure to monitor the subsurface. So the ENOS project I would mention in particular did a study, and they decided that the change in pressure was actually a really sensitive parameter. It would help you decide if you had any impermeable barriers that were affecting the flow in the reservoir, or if you had anywhere where the CO₂ was escaping out, because you would see the changes in the pressure. So it's a really important and sensitive technique. Part of showing that the site is behaving as expected is showing that our models and our monitoring data match up, and that's really critical. So here we've got an example from the Frio test site. It was injection into a saline aquifer, and on the left you can see the model. This is what they thought would happen, and on the right you can see the data that they actually recovered. So they monitored reservoir saturation and cross-hole seismic, and they confirmed that they were seeing what they expected to see. And these techniques are improving all the time, and modelling is improving all the time. So it's really interesting to see the evolution of these techniques. I'd also like to mention the GoldenEye permit application. So this is a well-characterised system with multiple barriers to leakage. The location of the wells is known. And the GoldenEye storage permit was designed to address all of the requirements, both of the CCS directive and UK regulations. So the monitoring plan was based on containment risk assessment, and they modelled the potential response from different techniques and they decided which of those techniques would be most effective to deploy. And they decided that it was important to focus their efforts around the well bores because they felt that the wells were they didn't expect leakage, but they felt that the wells were the point where the risk was largest. They said that even if it did leak through the wells, we'd expect it to be a small seep, but they wanted to make sure that they could monitor that potential leakage risk. And here they looked at using optic fibres rather than conventional seismic as a low-cost monitoring solution. So they were looking at doing thorough characterisation, a survey after closure of the site, and then using multi-well BSP DAS around the wells to look at the zone just around in the reservoir as a long-term monitoring technique to prove that the site was closed. They could monitor it, and then they could hand over to the competent authority because the site was behaving as expected and moving towards long-term stability. I'm also going to do a little plug for the GeoEnergy testbed, which is one of the ECCSEL research facilities. I'm science lead for this facility, and we're hoping to do some CO₂ injection later this year, provided we can get the final agreements in place. We have an environmental permit to inject the CO₂, and we have planning permission from the local council to have the infrastructure at surface. So it's just a case of finalising the last few details before we undertake a small amount of CO₂ injection. So we're planning to inject a few tonnes, and the aim of the testbed is to look at migration of CO₂ in the subsurface as well as leakage. So we have 2 injection depths. The lower wall will be used to study migration using downhole sensors, and the upper wall will be used to study leakage using surface sensors. So we have an array focused around the 2 small injection wells, and we've got a very tight array because we're doing electrical resistivity tomography, which requires the wells to be close together, and is also the reason why the casings are plastic. So we've got our deep wells, we've got microseismic in this well, and we've got a shallow well here, which we're hoping will see some of the CO₂ coming through the shallow aquifer. We've got optic fibre installed on the wells, and you can see in the top right, this is a test of the distributed acoustic sensing. So we've got each fibre is daisy chained between 3 wells, and in this one you can see me jumping up and down on the manhole cover, so you can see that the vibrations were being felt at depth in the wells. We've also been doing a lot of work using the BGS developed electrical resistivity tomography system, and it's been incredibly complicated, but they are now happy to say that they have got a bit more of a handle on what's happening in the subsurface, and we're really looking forward to seeing the changes that will happen when we inject CO₂. And we're also undertaking groundwater monitoring, and we've done some seismic reflection and some vertical seismic profiles, and we've done some looking at the core rocks to see what the rocks look like and how we expect those to be affected by CO₂ injection. So that's just one of the facilities for ECCSEL and one of the ways of studying the subsurface, and I just thought I would finish off by showing some of the opportunities to use the ECCSEL facilities. And then I will hand over to Helen.
Thank you.
Thank you, Ceri. So yes, we're switching to Helen now, who will be the final presenter, and I hope relatively quick. Helen, if you're able.
Yes, Jonathan, of course. I'll do my best. So hopefully you can see my screen.
Yes, we can.
And is that in presentation mode now? It is now. And I'm just going to see if I can get it there as well. So I'm going to go with the laser pointer. Okay, so a very quick whistle-stop tour around near-surface gas monitoring. Then, in that case, as Ceri said, in the unlikely event that your gas has managed to migrate out of the site, out of the storage site into the complex, and then continues upwards. So the areas that we're talking about here are the shallow subsurface, the surface to atmosphere interface, and the near surface atmosphere. I'm also going to say just a couple of words about seabed and marine, because we've got a facility that that handles that as well. So really we're looking at soil gas, we're looking at the permanent and the survey type approaches. There are challenges. I won't lie to you, it's not always easy. One of the key issues is surface expression of any gas reaching the surface is unpredictable. It will pop up where you least expect it, and it might be a very discrete footprint. or it may be very diffuse footprint, so tracking it down can be tricky. There's a lot of natural variability in CO₂ and other determinants in the near surface environment, so that can be tricky for baseline work. We get spatial and temporal coverage issues because there's a lot of variability associated with those as well, and then there's the issue of interpreting the data. So I'll start with the walkovers of surveys, and as Ceri's just flagged up the GTB, the way we tend to approach these is in a grid sampling approach, and the image here is actually of the GTB from the top, and this is our soil gas survey points. They're about 20 metre spacing. We need to access the gas first of all. We use these 1.5 metre long probes. We hammer them into the ground to access the gas in the subsurface, and then it's a pretty easy and versatile method, because then it's just end of pipe meters and monitors, so we can measure a range of gases that we're interested in, and we can also add on to that collecting samples for noble gases and for isotopes, for example, and we can also collect gas for radon as well, just off the end of the pipe as a flow-through system. It isn't always as straightforward as we think, because I'm not going to point fingers at our previous speaker, but if you let a geophysicist at one of our soil gas spikes, this is what she'll do to it. And if it's not the geophysicist, then it can be the locals will use your equipment to scratch their backs on. So you need to keep an eye on your kit in the field, even if it's only there for a few minutes at a time. As we're collecting our soil gas measurements, we'll also co-locate our flux measurements as well. So this is actually at the Svelvik site, and we're measuring for CO₂ here, but nowadays we can also concurrently measure for methane as well. And that gives us it's an accumulation chamber method, which you are essentially just measuring the rate of increase of concentration in this chamber, and then you can calculate that to a flux for that particular site. There we go. So I've said the interpreting the data, although it's easy to collect, it isn't always very straightforward. It's certainly not trivial. So just hopefully you can see these, and certainly you'll be able to catch the slides later. What I'm trying to show here is that we've got one single site here that was for which we did a grid survey on 3 separate occasions over about a 12-month period. And what we're looking at here is the flux, and you can probably make out it's cold to hot colours are low to high flux, and they vary quite significantly even between on the same site and between those particular surveys. The box and whisker plots, if you're happy with those, shows you the sort of level of uncertainty and variability in the CO₂ flux alone. And it's fairly representative of the uncertainty associated with some of the other measurements that we take as well. Here you've got CO₂, O2, and methane measurements are all pretty variable. And the reason for that is these natural processes going on in the soils, and we can actually use the huge amounts of data that we do collect and plot those up and have a look at whether we can attribute what we're seeing to some of these natural processes. So this, of course, is Catherine Romanak's work, and what she did is she looked at the processes of biological respiration, which is this equation here, and oxidation of methane, which is the lower equation here. There is a relationship between oxygen and CO₂, 1-to-1 in the case of the respiration, and 2-to-1 in the case of the oxidation of methane. And if you plot your data, assuming that you can get good enough resolution down at the low end if you're on baseline work, which is another issue I haven't got time to go into, then you can see that, you know, in this particular case, we are looking at them plotting between the respiration and the oxidation lines. If we were looking at leakage, then we'd be plotting up here as an external source of CO₂. So as I said, variability in the data can be an issue. We can also look at that, and we can use the standard errors to have a look at how our sampling grid should be constructed and how tight our spacing might be. But that is still only, specific points in time. And what we really need to do is increase our spatial coverage. And we do that with some of these more agile methods. We spent many years actually working with the open path lasers. I think we started that in Weyburn. It's about 1.5 meters long piece of kit that will mount onto the front of basically anything you want to put it on. So here we've got a Land Rover, we've had them on quad bikes, and if you happen to have a man called Bob who's willing to carry them over some really tough terrain, then Bob will carry them for you as well. And the type of data that we get from the open path laser is this type of spatial plot. This is from Larkasee in Germany, which is a natural vent, and you can see that we're able to spot some of the more diffuse vents here. And then this is 2007. In 2008, we're starting to see some quite discrete and quite pronounced vents there as well. Increasingly, though, we're moving across to the customised cavity ring down spectrometer, mainly because these open path lasers are species specific, and we've got a bit more versatility with the CRDS in that we can measure for 4 determinants in one hit, and we've been using these as well at one of our Glasgow sites. So. Typically, again, mounted on a cart or on a quad bike, whatever it takes to get it mobile. But even then, we're still talking about a single point in time, and what we really need to be able to do is tie in those specific time points to what is happening over a longer period. So we need to account for our temporal variation. So we have analogues of our survey methods, the multi-chamber flux and the soil gas concentrations. This is from the Rome gas pro system. This is actually a gas clam, which is an industry standard for landfill. And you can see that we get pretty variable flux and similar for the CO2 in soil gas as well. Perhaps a slightly more novel approach would be eddy covariance, where you're taking continuous measurements of temperature, wind, humidity, pressure, as well as CO2. What you can do with that data is calculate the flux, or you can derive the flux from those variables if you have a modeler that's prepared to or able to do that for you. It's useful to have some of the ancillary measurements as well, anyway, even if you're not using EC. I'm not sure that we can still class scanning lasers emerging. Although they are being deployed more and more frequently, we've got them up in Canada at the CAMI site, and they've also been using similar types of approaches at Quest, of course. And the basic idea is that you have a scanning laser head, and you can just about make out in the background there one of these reflectors, and you're essentially bouncing laser on and off those reflectors. And this is actually methane. The CO2, as you might imagine, is a bit more noisy because you've got quite a high background, but this is the type of data that you will get. You can use some of the scanning lasers to get around having to do point measurements for flux. So you can. We had a paper out in 2020 looking at the field scale using the lasers and some modelling by our modeler Andy Barkwith. And then you can improve your agility with UAVs, fixed wing or rotary, or even a helicite these days, and you can improve your sensitivity and your range of parameters with some of the newer instrumental methods, and in this case it's a Picaro. And what would be really great is if we can use the Picaro isotope kit to analyse in the field. A lot of this
Helen, could I ask you to start wrapping up, please? So we've got
this is my last one slide. So just want to mention Latera, because this is where most of these methods have been developed alongside the University of Rome. It's in a caldera. It's a volcanic system and natural vents. So these systems are, of course, really helpful because they have, not background levels but high concentrations of CO2. So we can actually test some of these systems and also cross-calibrate and cross-compare. So that's onshore, and also very quickly offshore. The Panarea MATLAB facility as well is also available to access through ECCSEL. Again, it's actually a volcanic system, and we can also look at water column, seabed, and ecological impacts of CO₂ in that environment as well. And this is my very last slide, Jonathan, just wrapping up. So we've said that we're monitoring for leakage in the zone where we live. We've a wide variety of tools and techniques, some standard, some emerging to do that. It's often easy to collect, but sometimes difficult to interpret. It's worth doing though, because basically you've got boots and high-vis on the ground. People can see that you're monitoring, and that is helpful to engage and reassure local communities. And then there's a whole bunch of facilities in ECCSEL that will help you if you want to do work on monitoring. And that's me.
Thank you very much, Helen. If you are able to stop sharing, that would be good.
There we go.
I don't know how to stop the screen, but anyway, it doesn't matter too much. Okay, so thank you, Helen. Thank you, Ceri. Thank you, John, and thank you, Kevin. In reverse order, the floor now is really over to the audience to propose questions either through the chat or the questions function. I know that John has had to go on to another commitment now, but thankfully Kevin is here. So I would encourage people to write down your questions. We've had one so far, which is really, I think, for Ceri and possibly Helen, which is around how you select the different, which monitoring technologies do you select for your particular storage operation, and is there a sort of consensus over one technique being the preferred option in these different regulatory jurisdictions? Ceri, do you have a view?
So the tools are selected based on your monitoring aims. So first you're going to look at the site and characterize and understand what are you trying to achieve with your monitoring, how are you going to show the conformance and containment of your site. And then you would probably model the expected response from all of the tools that you're considering and try to do a cost-benefit analysis to decide which ones will offer you the best value for money, the most efficient monitoring program that you can possibly think of. And there isn't really a consensus on which technique is effective. So because the properties of the subsurface sites are so different. So for example, we see a lot of seismic data from Sleipner, but if you were looking at depleted gas fields, the properties of CO₂ and gas in the reservoir are too similar, so seismic would not be effective there. We go to the Insala site and we see they used INSAR data, so they looked at satellite data to see how the ground had moved. It was incredibly effective there, but that's because it's a land-based site and their rate of injection was high. So we see kind of all of the tools have got their place, and I think using the tools in combination is really important because each bit tells you a different piece of the puzzle and helps you answer the question of, is my site behaving as I expect it to? Helen, is there anything you want to add?
Yeah, I would say from the near surface point of view, I think initially we tend to, it's an English expression, maybe it won't translate, but we throw the kitchen sink at it to start with. So, you know, yes, I absolutely agree with Ceri. It depends really on what you're monitoring, but we would go in initially quite extensive, particularly if we're doing baseline work, because we appreciate that whatever you monitor for, you know, there's a good chance that, you know, sometime down the line that will breach, because it depends on how you set your thresholds, and you would need to be ready to explain that and justify it. However, although that seems like an expensive approach in the first instance, if you could start with that approach, say 2 or 3 years out to get all your baseline data, then as you start to move through your project phase, you can start to adapt that. And this is certainly what happened at Quest, and it also it's been happening at Decatur as well. So they have all of that contextual sort of information, and then they've refined it down to, well, okay, we don't really want to be doing grid sampling surveys every 3 months. We will do that maybe once a year, and they will focus on some of the continuous monitoring and some of the more novel techniques.
Yeah, okay, thank you very much. So there's still time for people to post questions in the chat function or on the questions panel. But while you're thinking about some questions, just from my own interest, really, Kevin, could I ask you a question about the emission of these nitrosamines? And you showed these nice dispersal patterns from the stack once these compounds get out into the atmosphere. I was just wondering, do you have a feel for how long-lived they are once they get out into the atmosphere, and then what the pathways might be to other receptors in the environment once they're there? I don't know if you could just, because I see that as being a bit of a link between the storage side and the capture side of the operation.
I don't directly have a number to hand for that sort of thing. I mean, in the context of what's happening in the atmosphere, if you had a good enough grasp of the chemistry and the rate coefficients involved, then you could work out half-lives and that sort of thing. What happens when they get deposited on the ground, if by precipitation or whatever, that's a whole different area, and it's sort of outside of what I'm really been working on, so I couldn't really give you an answer, to be honest. We need our research associate to say something more about the model.
Yeah. Do you see the those dispersion models were predicting, you know, I guess that's all based on wind, etc., etc. What sort of footprints are we looking at in those areas, and what sort of scale is there on those footprints?
I think that example that we had was, trying to look at it, it was of the order of plus or minus 5 kilometers for that range, but I don't have a feel for the context of what that particular model was set up for, to be honest.
Yeah. And a final question, if I can, Kevin. So at the Turk facility at the University of Sheffield facilities, do you have the capabilities for monitoring these nitrosamines, either post emission or within your solvents? Is that something that you routinely do?
Potentially we do. There's a suite of analytical equipment that's being installed there. Quite how we go about the difficulties of actually sampling is another question, though. But the actual analytical equipment to do that type of study would be in place.
Yes. Okay. Thank you. Thank you. Well, I'm not seeing many more or any more questions either in the chat or the questions panels here from the audience. So I think I shall wrap up now, as it's 2 o'clock. So first of all, thank you all to our panelists. They were very interesting talks. I was dredging up some of my chemistry from my undergraduate days to keep up with Kevin, which I almost did. But they were very, very interesting talks, and hopefully the audience has found those talks useful as well. I just encourage everybody to visit the ECCSEL website, where you can see a lot of the details of all the facilities that we have available to you. We also have some funding calls coming up that might support, not completely fund, but support some of your attendance, or some of your let's say your attendance at a research facility, if that was something you wanted to do. And please talk to anybody within ECCSEL via the ECCSEL website or your so-called national nodes or whoever, and they will be able to help you. So with that, I will conclude. Helen, did you want to say something?
Yeah, I just wanted to say, if you want to refresh on the webinar, it will be available on the ECCSEL YouTube channel as well. Very easy.
Yes, thank you for that. Good point. Yeah, and with that, I shall wish everybody a good afternoon, and thank you for attending today, and thank you again to the presenters and to OGS and Sotocarbo, who have organised all this for us. So thank you to everyone. Bye now.